Thank you very much, Phil. And thank you to everyone here for attending today. As Phil said, my name is Jerry Wiltse, and I am a developer on the Conan team at JFrog. For today's talk, I'll be providing some high-level explanations about the fundamentals of Conan, but I'll also be going through some actual code and live exercises to reflect what working with Conan is like in practice. So the link in the QR code shown here on this slide will take you to all the resources for this talk. The slides will be posted there, as well as the link to the video eventually once the video is posted on YouTube. And you can also rate this presentation and enter a raffle to win a Conan t-shirt. So we will now post the links in the Zoom chat, or in the StreamYard chat for those interested. We also want to share with you the dates of another event where I'll be speaking about Conan if you'd like to learn more. That is JFrog's annual DevOps conference called Swamp Up. We will be holding the event online this year, and we'll be running it twice, once for the US time zone and once for the EMEA time zone. And the EMEA dates are shown here at the bottom of this slide. Also, Ari has some additional information to share about Swamp Up, so he'll be sharing that in the chat. So Ari, thank you for that. For the exercises today that we'll be doing, I've created a reproducible environment which contains all of the files and examples, and I will use that environment to run these commands. The goal of the environment is that anyone here can clone the repository and run the exercises on their own, and the commands are all contained in the PDF of this presentation. So once you have the PDF, that should be all you need to go through and reproduce the examples that I'll show here. Of note, the environment is based on Docker, so you will need to have Docker installed. But as long as you have Docker, everything should work on Windows, Mac, or Linux. If you try things out and you have any difficulties, please feel free to open a GitHub issue on the repository shown here in the slide. So before I start doing examples, I do want to provide a brief introduction to Conan. If you don't already know, Conan is a package manager for C and C++. It's open source and published with an MIT license. It's also multi-platform, meaning it can run on Linux, Windows, and Mac OS, as well as anywhere else Python can run. So we have a lot of users using it on various Unix distros, so that's possible as well. Conan is designed to support all the popular build systems in C and C++, as well as unique and custom build systems, which is not an uncommon occurrence in enterprise C++ development environments. A lot of organizations develop their own build systems using a series of Python or Bash scripts, and Conan can be adapted to work with those as well. Conan is stable, which means that there are not breaking changes within major versions. That is to say, packages built with any Conan 1.x version will continue to work for all future 1.x versions after that. If there's a breaking change to the model, it won't be until Conan 2.x is released. Conan is also a very active open source project. It has several full-time developers sponsored by JFrog, as well as an active user community, which submits dozens of pull requests each month. And our Slack channel has about 1,200 members, and it is one of the most active Slack channels in the C++ language community Slack. Finally, the Conan team has created multiple interactive self-paced training courses. So if you want to learn more about Conan in depth with more exercises, we have resources for you. These courses are all completely free and courtesy of JFrog on their online training platform known as JFrog Academy. So the high-level design of Conan is fairly straightforward compared to other well-known package managers, such as NPM, PyPI, Maven, or apt and yum if you use Linux. It features the common concepts of a local repository, which will be used for local package operations, and then remote repositories for sharing packages with easy-to-use upload and download capabilities and commands. There's a central moderated repository, public repository, with open source packages, and that is known as ConanCenter. And Artifactory is a server application provided by JFrog, which can host such remote Conan repositories, and that's what we'll be using for our exercises today. Also of note, ConanCenter is simply a Conan repository hosted on Artifactory in the cloud. The hosting and moderation service for ConanCenter are both provided by JFrog. So while Conan is similar to other package managers in these high-level architecture features, it's also very unique in its package model in a few ways. The string shown in the box here of pkg 0/0.1 at user/channel, this is an example of what Conan refers to as a recipe reference. This is the most simple and logical identifier there is for a package in Conan. But one of the unique features about Conan is that this recipe reference can represent any number of separate physical binaries, which would be built with unique build configurations. This package model where a single identifier can represent any number of unique binaries, that's one of Conan's major innovations. So here's a little bit of how Conan manages to do that. In simple terms, when you run a build with Conan, it assigns a unique ID for the configuration. So each unique configuration gets a separate unique ID. This unique ID is called the package ID, and Conan uses that for various things throughout the build and packaging process. For example, the package ID is used as a fundamental part of the directory structure for storing Conan packages on disk. As you can see here in this example, the top box is a configuration where the shared setting or the shared option is set to false. The second box is the same, except the shared option is set to true. So this second configuration will build a shared library. The first configuration will build a static library. But you can see those both get completely unique package IDs, and they will be stored separately. They can live on disk together side by side, and you can switch between the two binaries at will without having to rebuild or worry about one overwriting the other. So the client and server also use the package ID as a matching mechanism when uploading and downloading the binaries between the client and the server. For most of the operations you do in Conan, you must specify a build configuration. It can either be specified explicitly or implicitly using defaults. But with this configuration, the Conan client will calculate the package IDs for each package in your dependency tree, and it will use them for the various interactions with the server. Also, once you've built or downloaded a specific binary for a package on your local machine, that binary can be used across any number of projects on that same machine with the same configuration without needing to be rebuilt. So with Conan, there's just no need to rebuild the same binary multiple times with the same configuration over and over, which is somewhat of a common practice historically in developer environments where setting up and managing cached builds and precompiled binaries is too tedious or complex. Conan makes that sort of thing attainable and easy to use now. As we said earlier, Conan uses the build configuration as the input for calculating those package IDs. So here are two more complete examples of Conan build configurations, which are generally referred to as profiles in Conan. So when you hear build configuration, you hear profiles, we use those terms interchangeably. So users can store profiles as simple text files in this format and then pass the file names to the various Conan commands. This can be much more manageable than passing each of these values to the Conan commands at the CLI, but you can do either, and both are supported. So we will use both of these profiles we show here in our upcoming exercises today. The big difference is the one on the left will be for Linux with GCC version 7, and we'll be building the release config of that. The other one is Windows with Visual Studio 16, and also the release build there. One final note about profiles is that they allow you to do something else which is very powerful on top of specifying the build configuration. They allow you to specify build tools which you wish to use and be made available in your builds. So this is done with the build requires section as highlighted in yellow. In this example, we've specified that we want our builds to use CMake version 3.19.0. So this syntax implies that there is a Conan package which was created previously, which contains CMake 3.19, and Conan will make that the CMake executable from that package available via the path environment variable. So you can therefore use build requires as an alternative to installing build tools such as CMake directly in your systems or your user systems or your CI build servers. You can specify all of the build tools potentially in your Conan profiles. For many build tools and in many environments, this strategy can offer a lot of advantages. There's a lot to say about build requires and how people use them, but we can't get through all of that today. So we're just going to say that we're using this one in our talk, and we'll talk a little bit more about it when we get to the point where we use it. So the last major innovation of Conan, which we're going to mention today, is the abstraction layer that it provides over build systems. When developing applications in a team, it's a typical requirement that each developer should be able to build the entire application from source, including all of its dependencies. But since many C and C++ libraries have multiple open source dependencies of their own, unfortunately, open source C and C++ dependencies can have unique and complex build systems, or scripts that have to be run before you run the build systems and things like that. So this knowledge of how to build each dependency and each transitive dependency is a major burden for C and C++ developers who really, most of the time, just want to focus on their C++ code and not the build systems of their dependencies. Historically, it's just a cost of doing business. It's just something that developers have had to learn. But Conan aims to reduce the burden on the developer. So once an open source project has been packaged with Conan, either by the community, a package that's available in the ConanCenter repository today, or one that your team or someone in your team has packaged for your organization, then the users of that package no longer need to know anything about its build system to use it correctly or to use it directly. They can just consume it via Conan, and the build system part is taken care of for them. So instead, users can just can run the Conan Install command, which we will show shortly. And yeah, Conan handles all of those complicated interactions, whether it's with CMake, B2 for Boost, or a make-based build system, Bazel, or some new build system that your developers have never heard of. The team doesn't need to know all of the possible build systems in the code base in order to use dependencies. So let's now start with the interactive exercises. For our first exercise, we're going to demonstrate a seemingly simple goal, which is to get and use an open source dependency from ConanCenter and use it in a CMake project. It's also worth noting that the dependency we're going to use happens to be Boost regex. And this is relevant because getting and using Boost libraries has historically been a non-trivial endeavor. So here we'll show how Conan makes that easier. And the key command that we're going to take away from this first exercise is Conan Install. Another note is that all of the exercises we're going to do today, as we said, we'll perform the exercise on Linux first using GCC, and we'll perform it a second time on Windows using the MSVC compiler. So the goal here is to demonstrate Conan's cross-platform capabilities and show how one package reference can contain any number of binaries for different OSs and different compilers and things like that. So as we get into this, we will run it twice, and we will see the difference. So here are all the files relevant for the exercise. First, we've got a single source file named regex.cpp, which includes boostregex.hpp. Next, we've got a file named conanfile.txt, and this file is the most simple and declarative way to use Conan to provide dependencies to a project. There is another way, which we will get to in the next exercise, but this is the trivial way to consume packages. So more specifically here, though, we're saying that we want to provide the dependency to our project, and our project is using CMake's find package feature. So that's denoted here under the generators block. It says CMake find package. That's telling Conan what build system we are going to consume Boost with. And then finally on the right, we have the CMake lists file, which tells CMake how to build our source. We can also see that we're indeed using CMake's find package feature here in the third line, and that it is locating Boost and specifically the Boost regex component. So notice that this CMake list file does not contain anything specific to Conan. There's no mention of Conan anywhere in the CMake file. This demonstrates that any existing CMake projects using find package can now use dependencies from Conan without needing any modifications to the CMake lists. This is noteworthy because the Conan team has had to work very hard for several years to achieve this capability of complete transparency with CMake's find package feature. It was a very difficult feature to accommodate, but we have done so within the last, I think, year. So it's a big achievement. So here are the commands for the exercise. Again, these commands are available in the slides, and you can run them yourself, and you can run them from the Git repository we showed earlier. The operative command here, again, is Conan Install, which you can see on the third line. So this will download all the dependencies listed in the Conan file we just showed, and it will also automatically download the transitive dependencies. So not just Boost, it will download anything that Boost requires. Conan will then generate a number of files to be used in the upcoming build. So one of those files is activate.sh, which we will use in the next command here, the fourth command. So remember that we talked about build requires? Well, the activate.sh script that's what exposes the CMake executable from the Conan package to our current shell. It prepends the bin directory from that package to our path environment variables. So this is how we can get access to executables like CMake and other build tools from our Conan package out to our shell. So we explain more about Conan's virtual environment features in the courses in the JFrog Academy. So if you want to learn more about this really cool feature, I strongly suggest you go check out the courses. So after we do the source activate, we can then run the CMake, and we just run the CMake commands as we normally would without Conan. So from this point forward, there's really nothing unique to Conan in these two lines, from the CMake invocation to the build invocation, and then to the running of the executable. None of this is dependent on Conan at this point. Well, none of this is any different than you would do without having Conan. So right, in this case, we run CMake ... This configures, if you're not familiar with CMake, this configures the project, and it generates a build system file for the project. The next line, CMake -- build, that invokes the build system that was generated, and it actually runs the build and builds the executable. The executable we will create is called regex_exe, and when we run that with the string shown here, we get an output which has been transformed by boost regex. So the string we will be passing for this exercise is intended to represent like an email subject. So we have subject : and then we have RE : and then the word Conan. And what we want to parse out is, what was this email about by the subject? And we want to print out, so we base that on the RE : part. And we say, okay, this was regarding Conan. It's a simple text transformation just to demonstrate the build and the execution model. Afterwards, we do a little bit of cleanup here, where we run a deactivate script, which undoes the work that was done in the activate script. Also, we have a note here in teal that the above uses the precompiled binaries from ConanCenter for boost and for its transitive dependencies. But alternatively, you could build some or all of the dependencies in the dependency tree by simply appending -- build and the keyword all, or even named packages from the dependency graph. So this is good to know. We'll talk a little bit more about that later. But a lot of people have the impression that using Conan forces the use of precompiled binaries, and that is not the case. So we want to highlight that today. As I said, we will be performing all of these exercises once in Linux and then once in Windows. Here are the same commands, but in Windows. And I will simply go through and highlight the differences from the previous slide. They're highlighted in green already, and just we'll make a few notes about them. In the previous slide, we use a folder called Build Linux. In the Windows example, we'll use a folder named Build Windows. The profile is different. We talked about the profile earlier. Instead of using the source activate.sh command for line 4, we will be using the call and activate.bat. There's a little difference in passing the current directory to CMake at the command line. So we do that using this syntax here on Windows. And there's an additional, when you're using the Visual Studio generator for CMake, there's an additional flag you have to pass, which is the config you want to use. Otherwise, it will default to debug, and we want the release build. And then finally, when we execute the application we've built, we have to use a subfolder with a backslash to get to the executable where it was produced by CMake. However, after that, everything else that is of substance is the same. So we pass the same string, we get the same output, and again, it's just a simple difference in the call syntax for scripts. Yeah, but other than that, it is very similar and virtually identical to the Linux example. And so we will now execute those commands at a real shell. Bear with me. As I bring up my shell, I am reminded that I should always point out that we are about to embark on live interactive exercises. And anytime you do live interactive exercises, there's the opportunity for technical difficulty. If we do run into any problems, I apologize in advance. And we do have some YouTube videos of this talk, which were done previously, where everything has worked. So we can refer you to those. So, all right, so let's start with the commands from the previous slide. We'll start by cloning the Git repo. And we will cd into that repo. We will use Docker to invoke the environment. Normally, on your machine, the first time you run it, if you do choose to do this demo yourself, it will take a little more time than that to build and start the environment. But here, I've built it previously, so it used cached versions of the layers for Docker. So now we will connect to our Docker container, which we have created just to give us access to Bash and a clean environment with no packages on it. It's never been used before. And so we're starting with a truly clean environment. So now we will cd to the examples folder, and we will make our build folder called build Linux. And now, as I said, I should do ls ... And see here, we have the CMake list file that we mentioned earlier. We have the Conan file.txt that we mentioned earlier, and we have our source file, regex.cpp. The commands are also included in these scripts if you want to see them a little more easily. But we will run now the Conan Install command, which will look at the Conan file.txt, and it will produce CMake files for the CMake build system. So Conan's default behavior, I will pause it now, is to first print out the configuration that we passed it so that we can verify. So we said our profile was Linux GCC 7 release, and here it has printed it out in the profile format to show us that that is in fact true. This is a very helpful feature for debugging. Additionally, we know that we listed boost as our first dependency, but as we can see, and it was the only dependency we listed, but as we can see, zlib and bzip2 are already being downloaded because you may or may not have known that boost depends on zlib and bzip2 transitively. So Conan will take care of all of that for us and automatically download everything that it needs in order to satisfy the boost dependency that we stated. Great, it has done all of the downloads. And then, as I said, Conan has generated files for CMake, and here they are all listed. It's generated a file named findcmake.cmake, findboost.cmake, one for OpenSSL, zlib, bzip2, and iconv. So these were all of the dependencies in the dependency tree, and Conan has generated the files that CMake needs to find them. It has also generated the activate.sh script that I mentioned, which we will now use by running the source activate.sh. You can see here that Conan has affected my shell. It has prepended it with this Conan env identifier to let me know that I am now in a virtual environment. I'm actually going to back out and do the deactivate because I want to demonstrate something else. the container that I am in already has CMake installed in the operating system the normal way using apt. So if I run CMake -- version, I see that I have CMake 3.91 available. And if I type which CMake, it will show me that it's been found in user bin CMake. However, when I activate the virtual environment for Conan with this script, now if I type which CMake, you can see the path has changed. It has now found CMake in a deep folder path, which is inside of Conan's cache. This is, you don't need to worry about the folder structure, but you can see this proves that CMake is being used from the Conan package. And if I type CMake -- version, you can see that it is version 3.19 as opposed to 3.9. Okay. So with that said, that's one of the novel, neat features and convenience features that Conan provides for build tools. So with that said, let us run CMake and pass the arguments that we said we would. So we can see, if we are familiar at all with, let me zoom out a little bit, with CMake's verbose output, which can be adjusted now as of the latest release. CMake is telling us that what it has found and where. And the great thing is it finds all of the boost components that it needs, because by the way, regex depends on a whole bunch of other components within boost, and it has told us all of the dependencies that it found from boost, where it found them, and they all appear to be inside the Conan cache. So that's great. With that said, we now can build our executable. And a little note about the system clock, but that's okay. Now we will run our executable, as we said before. We're going to pass it this simple string, and we should just get a transformed string, and there it is. So what was this email about? It was regarding Conan. Great. Okay. We will now deactivate, excuse me, deactivate our virtual environment and back our way out to the examples directory. Now we want to do the same exact exercise on Windows. I will zoom in. I will cd to the CP demo folder, go to the examples directory, and now we will go through this quickly because we hopefully got the gist of it last time. We are simply now inside of my Windows system installation and doing the same command. Now notice, as I said, I started the Docker container with Linux with a clean environment, but my local Windows environment was not clean. I already had packages downloaded and installed. And Conan tells me that in the log, that it was able to find boost, bzip2, libiconv, and zlib all in my local cache. So because I've built or used those before on this local machine, it did not have to re-download or rebuild them from source. It was very fast. So now, we can also see down below it's generated equivalent CMake files for all the dependencies, but it's also generated .bat files because it detected I was on Windows. I can now call activate.bat, and it has the same exact effect that it had on the Linux shell when we used the shell script. I can say where CMake, because in Windows they have to be a little bit different, and we can see that in Windows it actually has found two CMake executables on my path, but the first one is the one from the Conan cache. So the activate script prepends. So when I run, which CMake -- version now, 3.19.0. So great. Now I will run CMake -- build. Excuse me. No, I will run CMake to generate the build system files, CMake, and then next we will build the executable. There is our nice verbose CMake output telling us that it has found all of the .lib files for all of the boost components. You know, all we asked for was boost regex, but look how much implementation detail there is to using boost regex. And Conan takes care of all of this for you. You don't have to know it. It's already worked out. So now we are building our executable. You can see here that CMake behind the scenes uses a Visual Studio project, and it has produced this executable. As we said, it is in the release subfolder, and the file name is regex.exe, and so we will now call that. And we will pass it the same string we did on Linux. Here we are, we got it. So we've now done cross-platform build using Boost on Linux and then on Windows. We've done it all within just a few short minutes. I will now deactivate my virtual shell, and I will cd back so that I'm ready for the next exercise. Okay. So here were the key takeaways from the exercise. Conan Install is the operative command to get dependencies from Conan and use them in the build system for your project. We use CMake find package, but we could have listed any number of build systems under the generator section. We could have generated files for a wide variety of build systems, including custom build systems. Conan makes this process of getting and using dependencies in a project relatively simple, even with historically non-trivial dependencies such as Boost. So we used CMake, which has this particularly sophisticated dependency management feature of find package. But if you want to learn a little bit more about how to support custom build systems, please check out the documentation, and you can learn how to write a custom generator. Finally, ConanCenter provides many packages with popular C and C++ projects, and that includes precompiled binaries for many different platforms and build configurations. So I think we build 120 or so binaries for each open source library that we build, typically. So that includes Windows, Linux, Mac OS, Visual Studio, GCC, Clang, and Apple Clang on Mac OS. So a lot of binaries should be ready to go for you to test out. However, if we don't have a binary for the build configuration that you want to use, for example, if you're using Raspberry Pi or Arduino or some other embedded system, or you just want to use non-default options, that's fine. All you have to do is provide the -- build flag, and that will always go through all of your dependencies and build them all from source and put the generated binaries in your local cache. So it's truly as trivial as it could possibly be. And it's really important to understand this capability, because even if we do have the binaries for the configuration you want, there are still a lot of scenarios where you wouldn't want to use the precompiled binaries, where maybe you can't because of a corporate policy or a wide variety of other reasons that you just can't use the binaries you need to compile from source. So this is a really big feature that we always want to highlight. It's one of the most misunderstood things about Conan that I hear from users. That's why we do these kind of talks. Looks like we're doing all right on time. So before we do the next exercise, I want to talk about Conan Recipes a little bit. The next exercise will be all about using our first recipe, so we need to provide a little background. We're going to explain what a recipe is, and then show some examples of recipes. And then we're going to show the recipe that we'll be using for the exercise last. In simple terms, a recipe is a Python class which Conan will read and execute in order to create your Conan package. It's the instructions for how to create a package. Let's look at one. So as we said, it's a Python class. If you're not familiar with Python, the syntax is relatively easy to learn. The Conan specification, or the recipe specification, defines a number of standard method names. These method names all correspond to logical steps in the building process for a C and C++ project. For For example, we have the build method down here, which invokes the build system. We have a package method, which collects artifacts. There are a few other methods listed here, but the build and package method are the two that make sense to most people. So now I'll explain these other three methods that you might not have thought about before. So the requirements method is equivalent to the requirements block of the Conan file.txt that we saw earlier. This is where we declare our dependencies. One of the advantages of doing it inside of a Conan recipe as a Python file is that the recipe can contain conditional logic, for example, dependencies that are only dependencies for a certain platform. We get this fairly frequently, that the dependency tree is different on Windows versus Linux versus Mac. For example, on Linux, your project might depend on pthreads. But on Windows, you might need a third-party library to get pthreads, like pthreads Win32 or some others. So here you can have conditional logic based on operating system, compiler, etc. In the export sources method, the second method, we define which sources Conan will capture from the current directory where the Conan file lives, and that will be used in the build of the project. So it will copy all of the files listed in export sources into the build folder before performing the build. In the generate method, we produce the files for the build system, which contains all the variables about the dependencies. So in our previous example, we generated 4 find package files for CMake. When you're using a Conan file to create a package, that will take place in the generate step. In the build method, as I said earlier, we invoke the build system to actually build the sources into the binaries. And then in the package method, we capture the binary artifacts which were built, as well as any other necessary files, such as headers. And then finally, in the package info method, we declare the contents of the package for the consumers. For example, the names of the libraries that we built, the .lib or .a files or .so files, we can list those here. Also, the directory for the headers and the directory where the lib files go, as well as C++ preprocessor definitions. All of those can be defined in package info. We'll now see an example of that on the next slide. Okay, here's one where the methods are actually defined. So of note, the package being built here, the project uses CMake as its build system. So here in the generate method, we see that we're using two CMake classes, CMake toolchain and CMake deps. These are Python helper classes that make the invocations of CMake a little bit easier. Actually, excuse me. I'll get to those in a moment. Let me jump back. Yes, so you see these CMake classes, as well as this CMake class down here in the build method and another one down here in the package method. This recipe is an example of one where we have good support for the build system that's being used by this project. So we can provide these helper classes to make the recipe clean and to make it look concise. However, the next slide we will show is one that does not use CMake, and it uses a custom build system. So we'll show what a recipe looks like when the project does not use CMake. A lot of the open source recipes you find in ConanCenter will use different build systems that are not CMake, so the recipes look quite a bit different than this one. But this is a good example. If you use CMake in your organization, this is maybe the best case scenario of what your recipe might look like. Okay, so first in the requirements method, we declare our dependency on boost. The syntax is a little different than the one we saw in the Conan file.txt, but I think it's pretty intuitive syntax, and it's just you call the requires function. Next, in the export sources method, we declare that we should capture all the files in the working directory as potential sources for the build. So self.copy star copies everything from source, and we're going to have those available in our build directory when we run CMake. Next, we have that generate method, and as I said before, these two classes, they generate the CMake files that will be needed in the build step. The one file that it generates is called Conan toolchain.cmake. This contains variables translated from the Conan settings in our profile. The other one is find boost.cmake as an example. This sets all the paths to the boost files in the Conan cache, and it does one find.cmake file for each dependency in the graph. So, yeah. Excuse me. The build method uses another CMake helper class, and it's just called CMake. And this auto formats the CLI arguments for calling CMake at the command line. So what you would normally run if you were going to run it manually is like we did in the example before. We might pass the toolchain file that was generated in the generate method, and we might pass a number of other arguments to get the invocation that we want. CMake takes care of all of that for us, this CMake helper class. And all we have to do is call the configure method and then call the build method, and Conan makes sure that the command line call is correct, the spaces is correct, the quoting is correct, and so it's just nice to have a helper method. The package method also uses this helper class to invoke CMake from the CLI, this time using it to call the install target, which copies the results of the build from the build folder into the package folder. So this is kind of an esoteric feature. If you know CMake, you might understand what this does, but it basically sets the CMake install prefix to the right place in the Conan cache. We'll show a counterexample in the next slide. Now, finally, the package info method at the bottom declares to the consumers of this package all of this package's headers, libraries, and libs, and all the information about them. So what we see here is include ders is a list of folder names. So we're putting all of the headers from our project into a directory named include, and we're telling consumer packages that they need to search for headers in this directory, in the include subdirectory. We do the same thing for the lib directories to tell consumers where to find the libs. So the static libraries or the shared libraries that we might have generated in this project, they will be found in the lib directory. And here's the list of those files in the libs object here. So the name of this package is called mylib, and we're producing a static or shared library called mylib. And we're putting it in a lib directory, and its headers will be in the include directory. So let's see. Now let's look at the counterexample. So this one is very similar to the previous example, which used CMake. However, here we want to demonstrate what the recipe looks like with a custom build system, as I said before, where we don't have helper classes. So the first two functions are identical. We still require boost the same way. We still copy the sources the same way. But in the generate method, we would have to define our own custom function. And this is where I said defining custom generators can take place. So you can, if your build system can read from a YAML file or a JSON file or a text file that you've defined, you can write a function that generates that kind of file, and you would do all of that in the generate function. All of the variables from boost and the other transitive dependencies, all of the paths to the libs, the paths to the headers and things like that, that's all made available to you in this generate method, and it will be passed to your function. So again, in the courses in the JFrog Academy, we show how to do a custom generator. So definitely check that out. Now in the build method, whereas before we used that CMake helper class, here we show an example that you can just use the self.run function to invoke any command at your local shell. So you can run your custom build system, whatever your command line invocation is today, you can just spell it out here as a string, and it can be run. A lot of times you might see 10 or 15 lines of self.run because custom build systems often involve a lot of different command invocations. But you can do whatever you want in this build method. You can run as many commands as you want. And and that's how you would invoke a custom build system. Now, in the package method, last time, in the last slide, we used the CMake helper, which had assumed that an install target was defined in CMake, which already said what the outputs of the build system were and where they need to be copied to at runtime. Here, we don't have that. So here, we have to explicitly declare exactly what the files were that we want to copy, and what folder structure we want them to go into in our package. So what we're saying here is copy all headers in this first line to a folder named include. And find the source directory where it's going to copy from is the source is a folder called src. Now here we go through and we copy star.dll and we put them into a bin directory. We copy star.lib and we put it into a lib directory. We do the same for dilib.so and .a. Excuse me. And so what this is showing is that this package function will capture static or shared libraries, whether it's on Windows or Linux or Mac OS, and whatever the folder structure is that the build system produces, it's going to put all the files into a standard directory structure of include, bin, and lib. So this is sort of an example of what you might see in ConanCenter, where the build system might use a unique folder structure when it outputs the artifacts, the DLLs or the lib files. And so here we use wildcards to just say, find all the shared libraries, all the static libraries, put them into appropriate folders, and this defines the package structure. Now, finally, the package info method is identical to the CMake example, and it defines that we've put all the headers into an include directory, all the libs into a lib directory, and that we expect to have captured one library named mylib in the process. So it's important to point out that you could capture the artifacts of your build and the headers of your build in whatever directory structure you want. That is totally definable by you. However, all you have to do is define what that folder structure is inside of the package info method, and the consumers will understand the folder structure that you've built. They'll get that information in their build system files. So for our next exercise now, we will take the same project we used in the previous example, but we're going to package it. Instead of conanfile.txt, we're going to define a complete recipe, conanfile.py, that will look a lot like the examples we just showed. We're going to use the Conan Create command to build the package from this recipe. So whereas before the operative command was Conan Install, now we're going to demonstrate the Conan Create command, which creates a package. As a reminder, our source file was a simple CPP file that included boost regex, and our CMake list file over here on the right, that's identical as well, nothing specific to Conan. But the conanfile.py is a little too big to show on this slide, so we're going to show that on the next slide. So this is very similar to the generic CMake example we looked at earlier, but we've streamlined it now. So in the previous example, we wanted you to see more of the methods that are available for different cases you might have when packaging libraries. But this is a simple case, so the recipe looks relatively simple. We can see here that we've defined a generator, the CMake find package generator, similar to how we did in conanfile.txt. We said that self.requires boost, just like we did in our other examples. For our export sources, we copy all files from the source directory into the build folder, and then we use the CMake helper functions to invoke the build and package up the artifacts. So let's try that. As we said, we will run this once on Linux and once on Windows. So let's step through these commands briefly, and then I will run them at the shell. In this case, after we cd into the example folder, we really just have to run the Conan Create command. It's the first major command that we do, and it's the only command you need to do to create a package from a library. If you have a suitable Conan recipe written, you just run Conan Create, pass it the configuration you want to build, and it will create the package for you. It's relatively simple. The rest of these commands, from the third line down, are all there to test the package that we've created and make sure that it works the way we expect. So what we're going to do is we're going to make a directory just to run the executable that we built and packaged. So we will make this directory, then we will use that Conan Install command to state that we want to run the regex package, and we're going to give it the same profile we used before. Then we're going to use the source command like we did before and use an activate script. And this will put the path to the regex package on my path environment variable. And that's how I will execute regex.exe, which is inside the package, very, very similar to the way that we ran CMake in the previous example. So we can run build tools this way, and we can also invoke our built artifacts in the same way using Conan's virtual environment feature, which is what this is. Okay, so let's quickly show the Windows example. Again, only a few things are different. The name of the profile, the directory names, a little bit of the syntax for how we call our program, but more or less, the spirit of the flow is the same. So let's do that. Let's do it on Linux. Let's bring up our shell. And back over to our Linux shell. And we will say, make it a little bigger for you there. We will run our Conan Create, and we'll see what happens. Goes a little fast. I'm going to scroll up and step through it briefly, see how we're doing on time. Okay. There we go. We'll step through this backwards. So the last statement it says is that it created a package with this revision. It packaged one file, regex.exe, and let's see. And then up above that, we see that it used effectively the same process that it used for the previous exercise. It runs CMake, and CMake finds all of the same dependencies for boost and all of that stuff in the same locations. It's just that this time it writes the build files to a build directory in the Conan cache, and then it runs the build in that, and then it captures the artifact from that folder. Yeah, so everything else is the same as the Conan install. It's just now Conan is doing it and then running the build system and capturing the artifact after. So now let us see if that executable we built is valid and if we can do it. We will run the Conan Install command, now passing the package reference or the recipe reference as I called it earlier right here. This is what it built, and we are now Conan installing that. We're telling it we want the virtual run env generator, which will give us the activate script. And we are passing it the same profile that we used to build it. And there we go. It says, hey, I found this regex.exe. It was in your local cache already, so I didn't have to download it. And it tells me that it has generated a file called activaterun.sh. It also generates PowerShell scripts as well, but we will use the shell script. And just as before, the executable works and it transforms the string just like we desired. And if I type which regex.exe, we can confirm once again that we are running this application from this deep nested directory, but we didn't have to know what that directory was. We're just in some working directory, and we've used this script to sort of, if we also look at the path, path environment variable, we can see that it has, in this current virtual environment, in my current shell now, the path includes the path to regex, but it also includes the path of bzip2 in case there were tools there, libiconv. So it gets the whole, and it even says it up here that the path environment variable was appended. So yeah, so you can inspect what the Conan virtual environments are doing to your shell if you like. So now I can deactivate that, and my path has gone back to normal. Now I need to jump back up, and I need to delete the little test directory. Okay, I hope that made sense. We ran the executable and we proved that it worked from our cache. So I will now jump over to Windows and do the same thing. So yep, we have our CMake lists, our Conan file, and our regex.cpp and some miscellaneous scripts. Now we will run Conan Create. Again, this time on Windows. Again, it will find boost and all of the dependencies that are already in my cache. It doesn't need to re-download them. It's reusing them because I'm using the same configuration, making it really just a pleasant experience here. Also very fast. So now I won't spend too much time explaining because it is all exactly the same as we did before in Spirit. It's just on Windows. But you can see now the narrowing of the difference of the experience between developing on Linux and developing on Windows for these types of applications with a package manager like Conan. The Conan commands give a cross-platform, a single syntax for multiple platforms for doing all of these high-level operations. So here we're running our exe again on Windows with the same subject. We get the correct result. And if I type where regex exe_exe, we prove that it's in this directory which we just built. Well, we built it up here. Okay, I will now deactivate my up. Okay. We did the Linux, we did the Windows. Now we briefly want to recap what we've done. Here are the key takeaways. A Conan recipe is always named conanfile.py, and it contains the instructions for creating a Conan package for a project. It's a Python class with some standard method names, requirements for defining dependencies, export sources for defining what sources need to come into the build, a build method for defining how to invoke the build system, a package method for how to capture files from the build system, and a package info method which says these were the files and the folders that we captured, so that downstream consumer packages can link with the libs and include the headers and even find preprocessor definitions and other things as well. So this is the general structure of a Conan recipe. And Conan will call these methods in order appropriately when you run the Conan Create command, and the result will be a Conan package. So that's how you create a package. All right, finally, the last exercise. We've created the same package on Windows and on Linux, just with two different binaries. So now we're going to show how to upload those two binaries for the same package to a single Conan repository, a remote repository on Artifactory, and show how Conan's search command will list each of the binaries under that single package reference. We're going to show a couple quick commands. Conan remote list shows all of the remotes that we know about. Remote add to add a new remote. We're going to add from our demo environment this Artifactory CE, which is a free community edition, and it's designed for Conan repositories specifically. So if you're going to do any POC or trial with Conan, it's probably a good fit. And then, of course, we'll be doing the Conan upload command to push our binaries to our shared repository. So let's do that. We're going to just look at the defaults, then we're going to add our new repository. The third command is the way to log in to that repository. We only need that because we're going to try to upload packages. But for example, for ConanCenter, you don't need credentials. You can just download open source packages without any credentials. And then here we're going to upload our regex package. And I think the syntax is pretty straightforward for how to do that. We specify the remote that we want it to go to, Artifactory, and we're saying we're forcing it And then finally, the Conan search will show, we pass the R artifactory, that will show all of the regex packages that it finds on the remote after we upload. Now remember, we're going to upload twice. We're going to upload once from the Linux machine and then again from the Windows machine, and we should see one package after the first upload, and then we should see two binaries after the second upload. So let's try that. Let's do Linux first. If I do Conan remote list, I should only have the defaults. This was a clean container when I started. So the default is to have ConanCenter, and it's the only remote. Very straightforward. We add another remote. Then we Conan remote list. There it is. It's named Artifactory, and here's the URL. We provide credentials because we intend to upload. These are the default Artifactory credentials I'm using here. If you want to run Artifactory, you should change the credentials. And now we will upload. So I won't spend too much time on the log here, but I'll show that it does find and upload a package named with the reference that we expected to the remote Artifactory. First, it uploads the Conan file itself, which is in a tarball. And you can see that here. It also uploads the sources that we captured and a manifest file that lists all the files. But then it moves on to uploading the actual binary. So this was the package ID that we mentioned for the Linux build. And so it found one of those and it uploaded that one. So there was an upload of the high-level reference and the recipe, and then an upload of the binary. So let's now search. Let's see what the server says that it has now. So the server says, yes, I have a recipe called regex 0.1.0 at demo/demo. And it says that I have one package ID, one build configuration with binaries, and it even gives some nice information about what that binary is. It's built with GCC 7, release, 64-bit. It gives the information from the configuration. It also gives the full list of requirements. So the full list of transitive dependencies here. So we know we had boost, but this also tells us that it was built against bzip2 and what version, libiconv and what version, and zlib and what version. Okay. Very novel. There's even more information. You can give more flags and it will give you more detailed information. Let's jump over to Windows. Again, we just have one remote, ConanCenter. We add Artifactory, the same URL. We log in so that we can upload. And we upload. Okay, so it said it uploaded regex 0.1.0, and it found one binary on the Windows machine, and it uploaded that one. So now, if we do the search, we see it found existing recipe of regex 0.1.0 at demo, and we have two package IDs now. We have the Visual Studio Windows version 16 and the Linux one that we had before. And so now we can see that we have the idea of one package with any number of binaries built with any number of unique configurations stored in a repository that understands that relationship, and it understands the one-to-many matrix. So one last thing we're going to do is we've shown what it looks like at the command line, but now we are going to go into the Artifactory UI. We're going to browse the repository there. If I can get my browser to cooperate. So we log in with the default credentials. And we go to Artifactory, Artifacts. This was the repository that we uploaded to. There is our regex package, version 0.1.0. There can be other versions. Demo/demo, this is the channel. And now here we have what we see is the revision of the package that we built. And we see the two package IDs. This is the, once you get used to browsing down into the repository a little bit, Conan package info. So this is the Windows Visual Studio 16 binary. And here is the, obviously, the Linux one. And if we expand it, Artifactory is a very nice UI in that you can expand the tarball and you can actually look and see what is inside the tarball without downloading it and extracting it. So here we can see that we've captured the exe file on Windows and we've captured the executable file on Linux, which has no extension. So you can see now this is how it's structured from a file system perspective. You have a package and you have any number of these package binaries. The Conan file, incidentally, is captured inside the export folder. So this is a little bit of the anatomy of the repository. And let's see. And I think that that's really helpful to see. I'm trying to think if there are any other. So again, Artifactory has a very powerful web interface. There's a lot of cool things you can do in terms of managing your repository, setting up replication between repositories. JFrog now has pipelines, which is like a CI system that you can that is integrated, which makes it a lot easier to do CI level stuff. We also have security and compliance scanning for your Conan packages in Artifactory. So there is a lot of things to explore if you do get a hold of JFrog Artifactory Community Edition, and I definitely suggest that you do. So now let us jump back to our slides. And then to recap, Conan Upload provides an easy way for uploading packages that you've built to a remote repository. There are easy commands for managing the local list of remote repositories, and ConanCenter is the one that comes installed by default. We also learned that Conan has a local repository, often called the local cache, and that packages here can be shared by any number of projects on the local machine. So once you have Boost with a certain configuration, there's no reason to rebuild it. We explained that this strategy of local and remote repositories with simple commands for uploading and downloading is similar to other package managers. And that's kind of valuable because it provides a practical and familiar experience to developers who have used other package managers, but also build system engineers and CI engineers who have to manage CI pipelines. If they already know how to build pipelines for Java and Python and C#, it's a lot more intuitive to get a hold of Conan and implement something similar with Conan than it is for some other package managers that may exist for C++ that don't have this architecture. So following the industry standard for the overall architecture of a package manager was definitely, I think, a really great decision from the Conan development team in the early days. So finally, we demonstrated how Artifactory CE provides free and local hosting for Conan repositories and how fast and easy it is to set up an instance and start uploading packages to it. It takes all of 3 to 5 minutes to get an instance with a repository started. So really, really great. So that's all the exercises we have, which is a shame because there's so much more I would like to show. With that said, here are the best places to go to learn more about Conan. On the homepage at conan.io, you can find links to each of the following resources. Each is valuable in its own way, depending on your environment and your interests. So we hope you find them helpful. Also, if you just want to chat with me or the rest of the Conan team or other Conan users in the community, you can find us all on Slack in the CPP Lang community Slack workspace in the Conan channel. So #Conan, and we're all there. We're chatting every day. Users are there every day. So It's a great resource. I can't recommend it enough. And in closing, I just really want to say thank you to Phil for allowing me to come and present to you all today, and thank you all for attending. We hope the session was enjoyable and informative. And if it was, please feel free to mention us on Twitter or LinkedIn if you use those platforms. I think Phil has tweeted out something from CPP London, so feel free to like that if you attended and leave a note what you thought. But in any case, Phil, I think now would be a great time to start going through the Q&A and taking questions, if we have time.
Well, thank you, Jerry, for an excellent talk and very thought-provoking again. We definitely had a lot of discussion in the Q&A, well, questions in the Q&A. Hopefully there'll be some discussion following. We may not get through it all. There's actually 23 questions. That's quite a lot.
Oh my.
So what we'll probably do is, because Remo does allow people to upvote questions, we'll go through the top rated questions, and then I'll feed you the rest of them to maybe go through one by one after the session ends, if that's okay.
Okay. Yeah, that's great. Good idea.
So the number one question seems to be, how does Conan ensure diamond dependencies like boost are consistent for the entire build?
Really great question. And I'll go as fast as I can while also answering the questions. So within a Conan execution, in general, one of Conan's really sound features is its graph model, its dependency graph model. So it works extremely hard to ensure like no duplicate dependencies in the graph, no violations of one definition rule, that kind of thing. So there will only ever be one instance of boost in the main dependency graph. There's an asterisk there for cross-compiling scenarios and also build tool scenarios. But in the general case, Conan works very hard to reconcile if boost appears 10 times with 10 different versions and 10 different, as in 10 different other packages and recipes, it will force the caller to reconcile that down to one version. And in general, the way you do that, you override the version of any recipe, any dependency where there's a conflict, you override it in the end consumer recipe. So whatever package you're creating or building, you define it in there, which version you want, and it will override the rest. So all the rest will be ignored. Now, whether or not that works is a matter of the dependencies. So if something absolutely requires, boost 160, and you force it to use boost 174, it may not work. But from Conan's perspective, that's a problem of the source code in that library of that package. Conan will force, from a dependency perspective, that only one version of boost is there.
Okay.
Hope that answered the question.
It answers it for me. As a side note, it was quite nice that when you first started talking about transitive dependencies in your talk, I got a few extra emails come through for the JetBrains raffle. So,
right. I thought that was a very funny coincidence.
So the next question: can Conan be used to cross-compile and build bare metal C and C++ projects, for example, for microcontrollers and embedded devices?
Great question. I have used it myself to cross-compile to some real-time platforms. As long as there is a cross-compiler which goes from an operating system and platform that is supported where you can run Python and run Conan to your target platform of your microcontroller or embedded devices, Conan can build and cross-compile and package the binaries for it. So yes, we have lots of people doing cross-compiling today obviously for mobile platforms. Conan is popular. People are using it for Android and iOS. Cross-compilers are all over the place there. So it's definitely a supported case. And we actually spend a lot of time in the last 2 years, more so than previously, making sure that cross-compiling use cases are supported.
Great, good to know, thank you. So the next one, where does the Conan name come from?
That has 6 votes. Wow, everyone's curious. I'm going to let Diego answer that in the chat if he is still here.
Okay.
And we can move on to the next one.
All right. Recipes seem like they have the potential for malicious or subversive activities, new malicious recipes or subversion of existing recipe. What protections are there to guard against such mischief?
It's a good point. In any language, even in CMake files, for example, if you have the ability to call out to arbitrary shell commands, then a recipe can always be malicious. So for ConanCenter specifically, we have multiple moderators, multiple reviewers, and require minimum of 3 approvals for every recipe and every change to every recipe that goes into ConanCenter. It's a very arduous process. There are a lot of eyes looking at it, and it's very heavily guarded. But in terms of your own enterprise, a malicious user who can change a Conan file in your organization and in your code base, that's a security implication for your team. It's not something that is guarded against within the application. So,
yeah, it's definitely been a hot topic in the tech news recently, but
it's
always about some backdoor somewhere.
That's true. Yeah. So I think one of the big distinctions between ConanCenter as a central repository compared to PyPI and the Ruby system and NPM, where there have been a lot of malicious packages that were found and used by a lot of people and had to be removed immediately, they were public. There was no no moderation process for new packages coming in. If you create a new organization, create a new package, put it up there, anyone can start using it. And then people would start using it. So with Conan, it is just not that way at all. We carefully look at every package that comes in. We have discussions about security all the time. It's just a completely different ecosystem. Great question.
That's good to know. Thank you. So is it possible to use Conan for other languages and package systems, such as Cargo and Rust?
Yes, it's theoretically possible. In years past, we had done some proof of concepts to package Go binaries, and we even had it on the documentation about how you could theoretically use it to capture and share the Go binaries. It's just not that practical. There's not even I'd say like a universal acceptance of a single package manager in C++. Meanwhile, Cargo, Rust has Cargo, and it's widely accepted within that programming community. So there's not a lot of reason or push to go into other languages, but it's theoretically possible.
Okay. Is Conan tied only to Artifactory as its repository provider? I think you got to that towards the end.
Yeah, so I'll just say that the Conan codebase contains both the client code as well as a primitive Conan server, which before Conan was acquired by JFrog, it was the way that you hosted a Conan repository. It was with the open source server implementation. That still exists in the codebase. It is still technically supported and active and tested. And because it is open source like that, other vendors have created implementations of Conan repository server API. So I think there are some others out there. I won't name them, but you can search them and you can find them.
Great. I have a couple more questions. Are there any minimal generic C++ project templates available using Conan? For example, with usual developer tools integrated, build system, hierarchy, static analysis, and so on?
Yes. So obviously, this one says minimal. Obviously, if you go to ConanCenter and you can find the recipes at what's called ConanCenter Index, it's a Git repository with all of the open source recipes. There you can find advanced real world examples. I should also say there's the Conan new command, which does produce from template complete projects. So it gives you the CMake, the sources, the recipe, obviously, and it gives you everything you need. There's also an examples repo under the Conan organization on GitHub with a whole bunch of examples of different cases of Conan. So those are 3 good resources you can use.
Great, thank you. Let's make this the last one. Can Conan fetch packages from GitHub directly?
No, it cannot. There's good reasons for that. In the interest of time, I won't go too deep into them, but a package is an abstraction that is separate from the source control. And there's good reasons for that. If you want to read about cautionary tales, check out the Go language ecosystem and the Golang package management history. They tried doing package references via source control, via GitHub repos, and it has since changed. Their strategy now is different, a little more like perhaps Conan. So I think, it's a good question. We get that question a lot, and there's still discussion about what we can do related to GitHub, but there's nothing direct like that today.